Right. So let us recall that we were proving this proposition 673, and this is our exercise 671, the only exercise of this section. So far we have been able to prove part A, part C, and this first identity of part B is there in the text itself. It has been proved, and we got stuck in our proof of this second identity. Let's recall what happened briefly. We established a result like this now, while in our attempt to prove this second identity, we proved something like this. Say xn is a sequence of positive real numbers that is convergent, and its limit is also positive. Then for any rational number sigma, this limit exists. And it is equal to L to the power sigma. But when the time came for us to use this in the proof of this, we realized that we don't just need sigma to be rational, we need sigma to be real. And I said in the comments that one can, in fact, somewhat not in a very difficult manner, somewhat easily one can extend this to real sigma. Maybe it was my desperation to get the result, because I vaguely thought about a procedure that would allow me to make that extension. However, today I realized that that is not possible. One cannot just simply do that in a very easy manner. So that means I am stuck here with this. Now whatever we have done so far in our proof or in our solution allows us to have this identity when R is rational, but that clearly is not enough. We want this to be true for real R. Now the thing here is this: since this is a standard identity, its proof will be available somewhere in the analysis literature. I just have to find it. Okay, so for now what we will do, we will assume it to be true and then complete parts D and E, thus completing the section. We will come back to it later. Okay, I will do something about it, don't worry. Since this is something that is there, I mean, it's not that we have to prove it, then only it will become a result. It's not like that. It is already available somewhere, we just have to find it. Or maybe I may come up with some idea that actually works. So today let us prove part D. And assuming this second identity of part B also means that we will use it wherever we need it, okay, without any proof. We will have to wait for that proof. Okay, now to prove part D, let's first see what we have in part D. Here q is greater than 0, that means our real number q is now positive. Then x is greater than y if and only if the corresponding qth powers are also related like that. So here the thing starts like this. First, assume x to be greater than y. Our aim is to prove that x to the power q is greater than y to the power q. Since q is greater than 0, we can assume without loss of generality that Qn is greater than 0 for all n greater than or equal to 1. Do you remember what Qn is? In the beginning of this proof, because Q is a real number, it is the limit of some sequence of rational numbers. That one such sequence is Qn. We assumed this in the beginning itself. Now here this extra condition Q greater than 0 means that there is a sequence of rational numbers converging to Q that is positively bounded away from 0, and that in turn means that there is a sequence of rational numbers converging to Q, all of whose terms are positive rational numbers. And so that's why we are saying that Qn that we chose in the beginning, we are choosing it to be such a sequence, okay, positively bounded away from 0, and hence all its terms are positive without losing generality. Such a sequence will always exist. So now the Qn's are rational numbers and they are all positive, so we can apply our corresponding result. We have a result corresponding to this part D for rational exponents that we can now apply. Then x to the power Qn is greater than y to the power Qn for all n greater than or equal to 1, and it is lemma 569, no? Yes, lemma 569 part D. Here also we have this corresponding result part D, that's what we are proving. Okay, so now we take limit on both sides using the comparison principle. So by lemma 6, 4, 13 or 13, which is the comparison principle, x to the power q, which is the limit of x to the power qn, is greater than or equal to the limit of y to the power qn that is equal to y to the power q. In the comparison principle, we just have inequalities like this. We don't have strict inequalities. So at once we cannot conclude that x to the power q is strictly greater than y to the power q. We have to work more for that. And that's what we are going to do next. Suppose x to the power q is actually equal to y to the power q. Then by the second, see here we need this. Of part B, we have this. X is x to the power 1, and that can be written as x to the power q times 1 over q Okay, and x to the power q times 1 over q, and in this step we are going to use this second identity, is the qth root of the power x to the power q. Now you use this thing, x to the power q and y to the power q are the same real number, so they will have the same qth root. Again use the second identity, so that is y to the power 1, that is equal to y. And this of course is a contradiction. It contradicts our assumption that our hypothesis here that x is greater than y. This line would be okay here. This contradicts so our supposition is wrong. That is, these two are not equal, but we already have this inequality, so that means x to the power q is strictly greater than y to the power q. That is 1/2, that's not the whole thing. Greater than y to the power q. Now we have to prove the converse. Conversely, assume this. Now in this case you will see that the converse, it's a little surprising that the converse actually follows from the other statement of which it is a converse. You treat this itself as x and this itself as y, this entire power, and then raise both sides to the power 1 over q. Just like q is a positive real number, 1 over q is also a positive real number. Since one over q is greater than 0 by what we have proved above, x is equal to, again we are using that second identity. this is greater than this. This inequality comes from what we have proved above. Okay. Thinking of x to the power q as x, y to the power q as y, and 1 over q as q in place of q. Again, use the second identity. So this directly gives you the fact that if this is true, then x is also greater than y. So they are equivalent. X is greater than y if and only if x to the power cube is greater than y to the power cube, and that is part D. Then we come to part E. Part E has two parts in it. When x is greater than 1, something happens, and when x is less than 1, something happens. Now here in part E, as opposed to part D, the base is same. In these powers, the base is x. In part D, the base was different. The exponent was same. Here the base is same, the exponents are different. So we are going to first of all consider x greater than 1. First, assume x to be greater than 1. Okay, so we have to prove here also to just under this condition itself, there are two things to prove. If q is greater than r, then this, and if this happens, then q is greater than r. So let's assume q to be greater than r. So this is our starting point. Then q minus r is a positive real number, and so there exists a sequence of rational numbers. Yeah, because q minus r is a positive real number, it will be the limit of a sequence of rational numbers that is positively bounded away from 0. There exists a sequence, say Sn, of rational numbers that is positively bounded away from 0. And this time we are not just simply going to use the consequence of this thing that all the Sns are positive. We are in fact actually going to use the full thing, what it means for a sequence to be positively bounded away from 0. It means that all the terms are actually greater than some positive rational number. Let C be a positive rational number such that xn is greater than or equal to C. Do we have greater yes? Oh, it's not Xn, sorry. It is Sn. Sn is greater than or equal to C for all positive integers n. That's what positively bounded away from 0 means. Then by lemma 569e, that means this result where the exponents are rational numbers, that is lemma 569 part E, and lemma 671 due to incessant rain, the humidity level is high, so everything is a bit messy. Lemma 671. What is the conclusion? Oh, x to the power Sn is greater than or equal to x to the power C, which is strictly greater than x to the power 0, and that is equal to 1. Okay, for this, I mean, in place of this inequality, to get this one, we have used part E of lemma 569. Just like that, to get this inequality also we have used it. Note that C is strictly greater than 0, and we do have, just like what you see here, we have strict inequalities. In lemma 569 part E also we have strict inequalities. Okay, so we will have strict inequality here. Okay, but then what is the need of lemma 671? I don't exactly remember lemma 671. Lemma 671. Lemma 671 is available here in this section only, no? And it is that main thing, no? Which says that if you have a sequence of rational numbers, say Qn, then this sequence is convergent. Why have we needed it here? Anyway, you see, you will understand. Okay, if we need it or not here, that you will understand. Right now I can't see its use here. It seems like lemma 569 part E is enough to write this. We will see. I mean, you go through this thing and you will realize whether we do need it. For all positive integers n. Okay. This implies by lemma 6/13 comparison principle. That x to the power q minus r, which is the limit of this sequence this is greater than or equal to x to the power c. To emphasize the fact that we have taken limits on both sides, let's just use limit on this side also. Okay, and because this is a constant sequence of real numbers, the limit is x to the power c, and this is greater than 1. So we have proved that x to the power q minus r is strictly greater than 1. Do you see that? Hence, by the first identity of part B, what we can now do, we can multiply on both sides by x to the power r. Well, not just simply by the first identity of part B, we also need part A. We have this x to the power q is this, which is equal to this, and that is greater than x to the power r. This step of course is obvious. In this step we have used the first identity of part B, and in this inequality we have multiplied both sides of this inequality, x to the power q minus r strictly greater than 1 by x to the power r, and the inequality stays like this because x to the power r by part A is positive. That is why. So what we have shown here is that if x is greater than 1, then q greater than r implies x to the power q is greater than x to the power r. Now the converse. Conversely, assume that x to the power q is greater than x to the power r. Okay, our aim is to show what? That q is strictly greater than r. If that is not the case, then q will be less than or equal to r. If we suppose q to be less than or equal to r, then arguing like above, we will conclude that x to the power q is less than or equal to x to the power r. In fact, we don't have to do any, we don't have to argue also. If q is equal to r, then x to the power q is of course equal to x to the power r. They are the same thing. And if q is strictly less than r, then by what we have proved here, x to the power q will be strictly less than x to the power r. So we end up having this, and which directly contradicts this one. A contradiction. So we cannot suppose q to be less than or equal to r and must have q to be greater than r. So one half of part E has been proved, that if x is greater than 1, then these two inequalities are equivalent. If one of them is true, then so is the other. But now we go to the other part, if x is less than 1. Next, assume x to be less than 1. Then by so this one you can guess will actually follow from this part itself, because x is less than 1 but at the same time x is greater than 0. Keep that in mind. So x is positive, that means we can take the reciprocal of x, that will be greater than 1, and we then use the this half of part E to 1 over x. That will give us the result. Then 1 over x is greater than 1. So by what we have, proved above, this is the case. Q is less than r. We do have q less than r here, no? Yes. Q is less than r if and only if minus q is greater than minus r. If and only if one over x to the power minus q is greater than 1 over x to the power minus r. Right. Now, if and only if, there is no need to rush through things. Let us take one step at a time. 1 over x is actually x to the power minus 1, which follows from part C. And we can multiply this minus 1 and minus q. That follows from this second identity of part B. So doing that, we get this. So x to the power q is greater than x to the power r if and only if q is less than r. So we have got our equivalence of these two inequalities, and we have been able to take this step from here because 1 over x is greater than 1. It's a real number greater than 1. So that's just it. This completes the proof of this proposition. Only we have this yet to prove. Hopefully in the next video I will give you a proof. I have seen something on the net. Maybe I can make the ideas work. We will see. So in the next analysis video, next Sunday, we are going to start a series. Whether we get the proof of this or not, we are going to start infinite series, because we cannot dwell on this for so long. Okay, it will be done, but we will see. And so that is next Sunday. And this coming Tuesday, tomorrow there is no video. On Tuesday we have done what? We have already once again we have seen group theory. So field, we will see a field theory video from Herstein's topics in algebra. So with that I end this short video here. If you want to say something about these things or about anything related to mathematics, you can write in the comment section below, or you can mail me at my usual address. Some of you are doing, I am very happy for that. I will help you as much as I can. And with that I sign off. See you on Tuesday. This is me, Lucifer, from a mathematical room. Have a nice night.